Welcome to this soothing exploration of the science of atmospheric refraction, a captivating phenomenon that gently bends our perception of the world around us. As light travels through different layers of our atmosphere, it undergoes changes that lead to fascinating visual effects. From the shimmering mirages on hot roads to the vibrant hues of sunrises and sunsets, atmospheric refraction is a subtle yet profound aspect of our environment. In this calming journey, we will delve into the science behind these phenomena, allowing you to relax and unwind while learning about the delicate interplay between light and atmosphere. Let the gentle flow of information guide you into a state of tranquility as we explore the wonders of atmospheric refraction together. To begin our journey, we must first understand what refraction is and why it is significant in the realm of optics. Refraction occurs when light rays travel from one medium to another, causing a change in their speed and, subsequently, their direction. This bending of light is a fundamental concept in physics and is essential for understanding how we perceive the world around us. When light passes from air into water, for example, it slows down and bends towards the normal line, which is an imaginary line perpendicular to the surface at the point of incidence. Conversely, when light exits the water and re-enters the air, it speeds up and bends away from the normal line. This intricate dance of light is not only fascinating, but also crucial for numerous applications in our daily lives, including the design of lenses, glasses, and even cameras. The significance of refraction extends beyond mere optics. It plays a vital role in how we experience our environment. The atmosphere, composed of various layers with differing temperatures and densities, acts as a medium through which light travels. As light moves through these layers, it is refracted, leading to a range of visual effects that can alter our perception. For instance, as the sun sets on the horizon, we often witness a beautiful array of colors, from deep reds to soft oranges and purples. This phenomenon is not solely due to the scattering of light, but is also heavily influenced by atmospheric refraction. The light from the sun passes through different air layers, each with varying temperatures and densities, resulting in the bending of light rays and creating the stunning colors we see during twilight. Understanding the basic principles of refraction allows us to appreciate the complexity of light behavior in the atmosphere. The concept of the index of refraction is central to this understanding. The index of refraction is a dimensionless number that describes how much light bends when it enters a medium. It is defined as the ratio of the speed of light in a vacuum to the speed of light in the medium. For air, the index of refraction is approximately 1:3, while for water, it is around 1.33. This means that light travels slower in water than in air, causing it to bend more significantly as it transitions between these two mediums. The greater the difference in the index of refraction, the more pronounced the bending effect becomes. As we delve deeper into the science of atmospheric refraction, we find that temperature gradients play a crucial role in how light behaves in the atmosphere. The Earth's atmosphere is not uniform. It consists of layers that vary in temperature and density. This stratification creates a complex environment for light to navigate. For instance, on a hot day, the air near the ground becomes heated, while the air above remains cooler. This temperature difference creates a gradient that influences the path of light. When light travels from the cooler air into the warmer air, it bends upward, leading to the phenomenon known as a superior mirage, where objects appear elevated above their actual position. Conversely, on a cold day, the opposite effect can occur. The cooler air near the ground can cause light rays to bend downwards, resulting in an inferior mirage, where objects appear lower than they truly are. These mirages are not mere illusions. They are tangible effects of atmospheric refraction that can be observed in various environments, particularly over bodies of water or hot surfaces. Such phenomena remind us that our perception of reality is often shaped by the intricate workings of light and atmosphere. Humidity and pressure also contribute to the fascinating effects of atmospheric refraction. The presence of water vapor in the air can alter the index of refraction, further influencing how light bends as it travels through the atmosphere. High humidity can lead to increased refraction, enhancing the visual effects we observe, such as halos around the sun or moon. Similarly, changes in atmospheric pressure can impact the density of air layers, affecting the bending of light. Understanding these factors allows us to appreciate the delicate balance within our atmosphere and the beautiful visual phenomena it creates. As we continue to explore the science of atmospheric refraction, it is essential to recognize its practical applications. The principles of refraction are integral to various fields, including meteorology, astronomy, and even photography. Meteorologists utilize knowledge of atmospheric refraction to predict weather patterns and phenomena such as rainbows and halos. Astronomers must account for refraction when observing celestial bodies, as the bending of light can impact the apparent position of stars and planets in the sky. Photographers rely on the principles of refraction to capture stunning images that reflect the beauty of the natural world, making use of lenses that manipulate light to enhance their photographs. In conclusion, the science of atmospheric refraction reveals the intricate relationship between light and the atmosphere. By understanding the basic principles of refraction, including the impact of temperature gradients, humidity, and pressure, we gain insight into the fascinating visual effects that shape our perception of the world. As we continue our journey through the wonders of atmospheric refraction, we will delve into historical perspectives, exploring the evolution of our understanding of this phenomenon and the key figures who have contributed to its study. Each step in this exploration brings us closer to appreciating the delicate interplay between light and atmosphere, guiding us toward a deeper understanding of the science that underlies the beauty of our environment. Let us now embark on the next phase of our exploration, where we will uncover the rich history of refraction studies and the remarkable individuals who have shaped our understanding of this captivating phenomenon. As we continue our exploration of atmospheric refraction, we delve into the historical perspectives that have shaped our understanding of this fascinating phenomenon. The study of light and its interactions with various mediums has a rich history, filled with influential figures whose discoveries laid the groundwork for modern optics. The journey through time reveals how our knowledge has evolved and how it has been impacted by the context of its time. One of the earliest discussions of refraction can be traced back to ancient civilizations. The Greeks, particularly philosophers such as Euclid and Ptolemy, pondered the nature of light and vision. They speculated about the behavior of light as it traveled from objects to the eye, laying the initial philosophical foundations for understanding how we perceive the world around us. These early ideas were more philosophical than scientific, lacking the rigorous experimentation that would come later. In the 17th century, the scientific revolution began to take shape, and with it came a more systematic approach to studying refraction. One of the key figures during this time was René Descartes, a French philosopher and mathematician. Descartes made significant contributions to our understanding of light by conducting experiments that demonstrated the bending of light as it passed through different substances. His work culminated in the formulation of what is now known as Snell's law, named after the Dutch mathematician Willebrord Snellius, who independently discovered the same principles around the same time. Snell's law quantitatively describes how light bends when it travels from one medium to another, establishing a mathematical relationship between the angles of incidence and refraction, as well as the indices of refraction of the two media involved. This was a pivotal moment in the study of optics, as it provided a clear framework for understanding how light behaves in various environments. The implications of Snell's law extended beyond mere academic curiosity. They had practical applications in fields such as astronomy and navigation. The ability to predict how light would bend when passing through the atmosphere allowed for more accurate celestial observations, which were essential for navigation and timekeeping. As we move further into the 18th century, the study of refraction continued to flourish. The work of scientists such as Isaac Newton and Christian Huygens further advanced our understanding of light. Newton's experiments with prisms demonstrated that white light is composed of a spectrum of colors, each bending at different angles when passing through a prism. This discovery not only deepened our understanding of light, but also highlighted the importance of refraction in creating the beautiful phenomena we observe, such as rainbows. Huygens, on the other hand, proposed a wave theory of light that complemented the particle theory put forth by Newton. His theory suggested that light behaves as a wave, and this perspective opened up new avenues for understanding how light interacts with various mediums. The wave nature of light would later become a cornerstone of modern physics, influencing the development of theories that explain refraction in terms of wave behavior. The 19th century brought about even more advancements in the study of refraction, particularly with the advent of new technologies and experimental methods. The invention of the telescope and microscope allowed scientists to observe the effects of refraction on a much smaller scale. This period also saw the emergence of the field of spectroscopy, which focuses on the interaction of light with matter. Spectroscopy further expanded our understanding of the properties of light and how they relate to atmospheric phenomena. As researchers continued to investigate the properties of light, they began to uncover more complex interactions between light and the atmosphere. The impact of temperature, pressure, and humidity on light's path became a focal point in the study of atmospheric refraction. Scientists recognized that the atmosphere is not a uniform medium. Instead, it consists of varying layers, each with its own characteristics. These layers can significantly influence the way light travels, leading to the beautiful and sometimes perplexing optical phenomena that we observe in nature. The 20th century marked a turning point in our understanding of atmospheric refraction as advancements in technology allowed for more precise measurements and observations. The development of satellites and sophisticated imaging techniques provided new insights into the behavior of light in the atmosphere. Researchers began to quantify the effects of atmospheric conditions on light travel, which was vital for improving weather forecasting and understanding climate patterns. In contemporary studies, the significance of atmospheric refraction extends beyond mere academic interest. It has practical implications for various fields, including meteorology, aviation, and astronomy. Understanding how light bends in the atmosphere helps meteorologists predict weather patterns. While pilots rely on this knowledge for navigation, astronomers must account for refraction when observing celestial bodies, ensuring accurate measurements and observations. As we reflect on the historical journey of atmospheric refraction, it becomes clear that our understanding has been shaped by the contributions of many brilliant minds. Each discovery has built upon the last, creating a rich tapestry of knowledge that continues to evolve. The interplay between scientific inquiry and historical context has been crucial in advancing our comprehension of light and its behavior in the atmosphere. In conclusion, the exploration of the historical perspectives on atmospheric refraction reveals a fascinating evolution of thought, from the philosophical musings of ancient civilizations to the rigorous scientific methods of modern times. We have come to appreciate the complexities of light and its interactions with the atmosphere. As we move forward in our journey, we will delve deeper into the scientific principles that govern light waves and their behavior in various mediums, further enriching our understanding of atmospheric refraction. Let the soothing rhythm of this exploration guide you into a tranquil state of mind as we continue to uncover the wonders of the natural world around us. As we immerse ourselves further into the captivating world of atmospheric refraction, let us explore the intricate relationship between light and the atmosphere itself. This delicate interplay defines not only how we perceive the world, but also how celestial phenomena unfold above us. To understand this, we must first consider the structure of our atmosphere. It is divided into several layers, each characterized by distinct properties, including temperature, pressure, and density. These layers interact with light in unique ways, leading to fascinating visual experiences. At the very surface, we have the troposphere, which extends from the Earth's surface up to about 8 to 15 kilometers high. This is where we experience most of our weather and where clouds form. The air in the troposphere is warmer at the bottom and cooler at the top. This temperature gradient plays a crucial role in how light is refracted. When light passes through this layer, it bends toward the denser, cooler air, causing objects to appear distorted. This bending of light can create various optical illusions, such as the shimmering effect we see on hot days, where distant objects seem to waver or ripple. Above the troposphere lies the stratosphere, extending up to about 50 kilometers. This layer contains the ozone layer, which absorbs and scatters ultraviolet solar radiation. The temperature in the stratosphere increases with altitude, creating a stable layer of air. As light moves through this layer, it encounters less turbulence and more consistent refractive effects. The refractive index in the stratosphere differs from that in the troposphere, leading to variations in how we perceive distant objects. This stability can enhance the clarity of distant celestial bodies, allowing for clearer views of stars and planets. Further up, the mesosphere extends to about 80 kilometers above the Earth. Here, temperatures decrease again, and the air becomes increasingly thin. The refractive properties of light in the mesosphere are less pronounced due to the reduced density of the atmosphere. However, phenomena such as noctilucent clouds, which occur in this layer, can create stunning displays of light due to the scattering of sunlight against these ice crystals at high altitudes. The intricate balance of temperature and density continues to influence how light travels through the atmosphere, resulting in varied visual experiences. As we transition to the thermosphere, which can extend up to 600 kilometers, we encounter a layer where the air is incredibly thin and temperatures soar high due to solar radiation. In this layer, the refractive effects of light become less relevant to our everyday experiences, as the density is too low to significantly bend light in a manner that affects our perception of celestial bodies. Instead, the thermosphere is where we find phenomena such as the auroras, which are created by charged particles from the sun interacting with the Earth's magnetic field and atmosphere. The vibrant displays of light in the auroras are a reminder of the complex interactions between light and our atmosphere. Returning to the troposphere, we must also consider the impact of humidity and pressure on light refraction. Humidity refers to the amount of water vapor present in the air, and it can significantly alter the refractive index. When humidity levels are high, the air becomes less dense, which can lead to increased bending of light. This is particularly noticeable when observing distant objects over water, where the humidity can create a mirage effect, causing objects to appear floating or distorted. Pressure also plays a vital role in atmospheric refraction. The relationship between pressure and density is crucial for understanding how light behaves as it travels through various layers of the atmosphere. High pressure typically leads to clearer skies and more stable atmospheric conditions, resulting in less scattering of light. Conversely, low pressure systems can result in turbulent air, which can scatter light in unpredictable ways, leading to a variety of visual effects such as halos around the sun or moon, or even the appearance of sundogs, which are bright spots that appear on either side of the sun. As we delve deeper into the phenomenon of atmospheric refraction, we must also explore the concept of angular refraction. This refers to the angle at which light bends when entering a different medium. When light enters the atmosphere from space, it does so at a certain angle. As it passes through the layers of the atmosphere, each with its own density and temperature characteristics, The light bends at different angles. This bending can cause celestial objects to appear higher in the sky than they actually are, a phenomenon that is particularly notable during sunrise and sunset. The significance of angular refraction cannot be overstated, particularly in the field of astronomy. When stargazers observe the night sky, they are seeing celestial bodies that are not exactly where they appear to be. The bending of light caused by the atmosphere alters the apparent position of stars and planets. This effect is more pronounced when observing them near the horizon, where the light travels through a greater thickness of atmosphere. Understanding this aspect of refraction is essential for astronomers, who must account for it when making observations and calculations. In addition to angular refraction, we must also consider the concept of total internal reflection, which occurs under specific conditions. This phenomenon can happen when light travels from a denser medium to a less dense medium at a steep angle. Instead of passing through, the light is reflected back into the denser medium. Although this concept is more commonly associated with optical fibers and lenses, it plays a role in atmospheric phenomena as well. For instance, when light travels through layers of air with varying temperatures, it can reflect off the boundary between these layers, creating stunning visual effects such as the green flash observed just before sunset. As we explore the various aspects of atmospheric refraction, it becomes apparent that this phenomenon is not merely a scientific curiosity. It has practical implications that affect our daily lives and experiences. For example, pilots must account for atmospheric refraction when navigating through the skies. The bending of light can alter the perceived position of the horizon, which is crucial for maintaining altitude and orientation. Similarly, mariners rely on an understanding of refraction when using celestial navigation, ensuring that their calculations are accurate despite the effects of the atmosphere. In the realm of photography, the principles of refraction are also at play. Photographers often manipulate light to create stunning images, and understanding how light bends can enhance their artistry. Lenses are designed to refract light in specific ways, allowing photographers to capture images with clarity and depth. The art of capturing the perfect sunset, for instance, relies on the photographer's ability to understand how light interacts with the atmosphere, leading to breathtaking hues and contrasts. As we continue our exploration of atmospheric refraction, we encounter the fascinating phenomenon of halos. Halos are bright rings that encircle the sun or moon, caused by the refraction of light through ice crystals in the atmosphere. These ice crystals can be found in cirrus clouds at high altitudes, and their hexagonal structure plays a crucial role in creating these optical effects. The light bends as it passes through the crystals, resulting in the formation of halos that can vary in size and brightness. There are different types of halos, each with its unique characteristics. The most common is the 22-degree halo, which appears as a bright ring at an angle of approximately 22 degrees from the sun or moon. This halo is often accompanied by a secondary halo, which appears further out and is less bright. The beauty of these halos captivates observers and serves as a reminder of the intricate interactions between light and the atmosphere. In addition to halos, we must also explore the phenomenon of rainbows, which are among the most cherished optical effects created by this atmospheric refraction. Rainbows occur when sunlight is refracted, reflected, and dispersed through water droplets in the atmosphere. The process begins when light enters the droplet, bending as it passes from air into the denser water. Inside the droplet, the light reflects off the inner surface before exiting and bending again as it returns to the air. This combination of refraction and reflection results in the dispersion of light into its constituent colors, creating the vibrant arc of a rainbow. The colors of a rainbow follow a specific order known as the spectrum, which includes red, orange, yellow, green, blue, indigo, and violet. This sequence is a result of the varying wavelengths of light, with red light bending the least and violet light bending the most. The beauty of a rainbow serves not only as a visual delight, but also as a reminder of the science behind light and its interactions with the environment. As we delve deeper into the understanding of atmospheric refraction, we must also consider the broader implications of this phenomenon. It is essential to recognize that our perception of reality is often shaped by the way light interacts with the atmosphere. The bending of light can alter our understanding of distance, position, and even color. This realization invites us to appreciate the beauty and complexity of our environment. In conclusion, atmospheric refraction is a multifaceted phenomenon that encompasses a range of scientific principles and visual experiences. From the layers of the atmosphere that influence how light bends to the beautiful optical effects we observe, such as halos and rainbows, the interplay between light and atmosphere offers a profound understanding of our world. As we drift further into the soothing embrace of knowledge, let us carry with us the appreciation for the intricate dance of light and its ability to shape our perceptions. May the wonders of atmospheric refraction inspire our dreams and fill our minds with tranquility. Thank you for joining this exploration, and may your nights be peaceful, illuminated by the gentle glow of understanding. As we continue our exploration of the science of atmospheric refraction, let us delve deeper into the intricate ways in which the layers of our atmosphere influence the bending of light. Understanding how atmospheric layers affect light is crucial for grasping the phenomena we observe every day. The Earth's atmosphere is a complex structure, composed of several distinct layers, each with unique properties. These layers include the troposphere, stratosphere, mesosphere, thermosphere, and exosphere. Each layer plays a significant role in how light behaves as it travels through the atmosphere. The troposphere is the lowest layer, extending from the Earth's surface to about 8 to 15 kilometers above sea level. It is within this layer that most of the weather phenomena occur. The temperature in the troposphere generally decreases with altitude, leading to significant temperature gradients. This decrease in temperature contributes to the bending of light as it passes through different layers of air with varying densities. As light moves from warmer air to cooler air, it slows down and bends toward the denser medium. This bending is what creates many of the visual phenomena we associate with atmospheric refraction. In contrast, the stratosphere lies above the troposphere, extending to about 50 kilometers above the Earth's surface. Unlike the troposphere, the temperature in the stratosphere increases with altitude, primarily due to the presence of the ozone layer, which absorbs ultraviolet radiation from the sun. This unique temperature profile also affects how light behaves. As light travels through the stratosphere, it may experience less bending than in the troposphere, where temperature variations are more pronounced. Understanding these differences helps us appreciate how light is refracted differently as it ascends through the atmosphere. The mesosphere, which extends from about 50 to 80 kilometers above the Earth, is where temperatures begin to drop again. In this layer, light can be refracted further, particularly as it interacts with the various particles and gases present. As we ascend into this layer, the density of the atmosphere decreases, which can lead to more pronounced refraction effects. The thermosphere, reaching up to 600 kilometers, and the exosphere, which transitions into outer space, have even more complex interactions with light due to the lower density of particles. These layers can lead to unique optical phenomena, especially during certain conditions, such as solar activity. Temperature gradients in the atmosphere play a critical role in how light is refracted. When light travels from a layer of warm air into a layer of cooler air, it slows down, bending towards the cooler air. This bending can result in various visual effects, such as the apparent displacement of objects on the horizon. For instance, when looking at a distant object, such as a ship on the ocean, the ship may appear to be floating above the water due to the light bending around the warmer air near the surface. This phenomenon illustrates how atmospheric layers can create illusions, altering our perception of reality. Humidity and pressure are also significant factors influencing atmospheric refraction. Humidity refers to the amount of water vapor present in the air, which can affect the density of the atmosphere. When humidity levels are high, the air becomes less dense, which can alter the path of light. As light travels through humid air, it may bend differently compared to dry air. This variation can create optical effects, such as halos around the sun or moon, where light is refracted through water droplets in the atmosphere. Pressure, on the other hand, relates to the weight of the air above a given point. Changes in atmospheric pressure can lead to variations in air density, which, like temperature and humidity, can influence how light is refracted. For example, on a high-pressure day, when the air is more stable and dense, light may travel more directly, resulting in clearer visibility. Conversely, on low-pressure days, where the atmosphere can be more turbulent, light may bend more unpredictably, leading to hazier conditions. As we consider the implications of atmospheric layers, temperature gradients, humidity, and pressure on light refraction, it becomes clear that these factors work together to create the beautiful and sometimes surprising optical phenomena we observe. From the shimmering mirages seen on hot roads to the vibrant colors of a sunset, the interplay between light and our atmosphere is a delicate dance that shapes our visual experience of the world. Mirages, for example, are a fascinating manifestation of atmospheric refraction. They occur when layers of air at different temperatures create a gradient that bends light rays. In the case of an inferior mirage, which is commonly seen on hot days, the ground is heated significantly by the sun. The warm air near the surface is less dense than the cooler air above it. As light rays travel from the sky to the ground, they bend upward when they encounter the warmer air. This bending can create the illusion of water on the road, where the sky is reflected, making it appear as though there is a pool of water, even when none exists. On the other hand, superior mirages occur under different conditions. These happen when the temperature of the air increases with altitude, which is the opposite of what typically occurs. When light passes through this cooler air and then into the warmer air above, it can bend downwards, creating the illusion of objects appearing above the horizon. Superior mirages can make distant ships appear as if they are floating in the air, or create images of landforms that are not actually present. Both types of mirages remind us of the remarkable ways in which our atmosphere can alter our perception of reality. In addition to mirages, atmospheric refraction gives rise to other optical phenomena, such as halos and rainbows. Halos are typically circular rings of light that appear around the sun or moon, caused by the refraction of light through ice crystals in the atmosphere. These ice crystals, often found in cirrus clouds, act like prisms, bending the light at specific angles and creating the beautiful halo effect. The size and brightness of halos can vary based on the atmospheric conditions and the orientation of the ice crystals. Rainbows, another stunning example of atmospheric refraction, occur when light is refracted, reflected, and dispersed through water droplets in the atmosphere. When sunlight enters a raindrop, it bends as it passes from air into the denser water. This bending separates the light into its component colors, creating a spectrum that forms a circular arc. The angle at which the light exits the droplet determines the colors we see, with red light bending the least and violet light bending the most. The result is the beautiful multicolored arc that we recognize as a rainbow. Understanding these phenomena not only enhances our appreciation for the beauty of nature, but also illustrates the complex interactions between light and the atmosphere. Each optical effect serves as a reminder of the intricate dance of light, temperature, humidity, and pressure that shapes our visual world. As we continue to uncover the science behind atmospheric refraction, we gain a deeper understanding of how these elements combine to create the stunning visual experiences that enrich our lives. Moreover, the implications of atmospheric refraction extend beyond mere visual phenomena. In fields such as astronomy, understanding how light is refracted in the atmosphere is crucial for accurate celestial observations. When astronomers observe stars and planets, they must account for the bending of light caused by the layers of air between the observer and the celestial bodies. This bending can alter the apparent position of stars, causing them to appear higher or lower in the sky than they actually are. Astronomers use various tools and methods to correct for atmospheric refraction, allowing for more precise measurements of celestial objects. One common technique involves using refraction models that take into account the temperature, pressure, and humidity of the atmosphere at the time of observation. By applying these models, astronomers can adjust their calculations, ensuring that they are observing the true positions of stars and planets. In addition to correcting for refraction in observations, understanding atmospheric conditions is essential for navigation. Sailors and pilots rely on accurate celestial navigation for positioning, and any distortions caused by atmospheric refraction can lead to errors. By taking refraction into account, navigators can ensure that they are accurately determining their location based on celestial bodies. As we reflect on the significance of atmospheric refraction, we recognize its pervasive influence in our daily lives. From the stunning visual phenomena that captivate our attention to the practical applications in navigation and astronomy, the science of atmospheric refraction is a testament to the interconnectedness of light and atmosphere. Each observation, whether it be a fleeting mirage on a hot day or the serene beauty of a rainbow after a rain shower, invites us to marvel at the complexities of our environment. In conclusion, our exploration of how atmospheric layers affect light has revealed the profound impact of temperature gradients, humidity, and pressure on the bending of light. Mirages, halos, and rainbows serve as reminders of the delicate interplay between light and the atmosphere, creating visual wonders that enrich our experiences. As we continue our journey through the science of atmospheric refraction, let us carry with us the knowledge of how these phenomena shape not only our perception of the world, but also our understanding of the intricate systems that govern our natural environment. Embracing this knowledge can deepen our appreciation for the beauty that surrounds us, encouraging us to observe the world with a sense of wonder and curiosity. As we prepare to transition into the next section of our exploration, let us take a moment to reflect on the captivating ways in which light interacts with our atmosphere. The intricate layers and their unique properties work in harmony to create the stunning optical phenomena we have discussed. By understanding these complexities, we can foster a greater appreciation for the beauty of atmospheric refraction in our daily lives. Let this newfound knowledge guide you into a state of tranquility as we continue to uncover the mysteries of the science of atmospheric refraction together. As we gently transition into our exploration of astronomical refraction, let us consider the vastness of the universe and our place within it. The stars and planets that adorn our night sky are not only beautiful to behold, they are also subject to the same phenomena that we have discussed in relation to atmospheric refraction. Just as light bends when it travels through different layers of the Earth's atmosphere, so too does it bend when it travels through the atmosphere of other celestial bodies. This bending of light plays a significant role in how we perceive the cosmos, influencing everything from the position of stars to the appearance of planets. To begin with, let us reflect on the nature of light itself. Light travels in straight lines through a uniform medium. However, when it encounters different densities, such as the varying layers of the Earth's atmosphere, it bends or refracts. This bending is not merely an optical curiosity, it has profound implications for astronomy. For example, When we observe a star on the horizon, the light from that star must pass through several layers of atmospheric density before it reaches our eyes. Each layer, with its distinct temperature and pressure, alters the path of the light, causing the star to appear higher in the sky than it actually is. This phenomenon is known as astronomical refraction. The significance of refraction in astronomy extends beyond just the visual perception of celestial objects. Astronomers must take atmospheric refraction into account when making precise measurements. The apparent position of a star can differ from its true position due to the bending of light. This discrepancy can lead to errors in navigation and celestial mapping if not properly accounted for. In fact, the correction for astronomical refraction is a crucial aspect of observational astronomy. It ensures that the data collected from telescopes accurately reflects the positions of celestial bodies. As we delve deeper into this subject, it is essential to recognize the factors that contribute to the degree of refraction experienced by light passing through Earth's atmosphere. One of the primary factors is the temperature gradient. The atmosphere is layered, with warmer air sitting above cooler air. When light travels from the cooler, denser layers of air to the warmer, less dense layers, it bends upwards. This is particularly evident during sunrise and sunset, when the sun appears to linger on the horizon longer than it actually does due to the bending of its light. Humidity and atmospheric pressure also play critical roles in the process of refraction. High humidity can increase the refractive index of the air, leading to more significant bending of light. Similarly, variations in atmospheric pressure can create different densities within the air layers, further influencing how light travels. For astronomers, understanding these atmospheric conditions is vital for accurate observations. They often rely on complex models and calculations to predict the degree of refraction based on real-time weather data. As we explore the impact of refraction on celestial observations, we can also consider how this knowledge has shaped our understanding of the universe. Historical navigators relied on celestial bodies for guidance, and any errors in their calculations due to refraction could have dire consequences. The development of more accurate instruments, such as the sextant, allowed navigators to measure angles more precisely, but they still had to account for the bending of light. In essence, the study of refraction has been intertwined with the advancement of navigation and astronomy for centuries. In modern astronomy, telescopes equipped with sophisticated technology help mitigate the effects of refraction. Adaptive optics, for instance, allow astronomers to adjust for atmospheric disturbances in real time. This technology compensates for the blurring effects created by refraction, enabling clearer images of distant celestial objects. The ability to observe celestial phenomena without the hindrance of atmospheric distortion represents a significant leap in our quest for knowledge about the universe. Moreover, astronomical refraction is not limited to the Earth. Each planet and moon has its own atmospheric characteristics that influence how light is refracted. For instance, the atmosphere of Venus is dense and composed mainly of carbon dioxide, which causes light to bend differently than it does in Earth's atmosphere. This unique refraction affects our observations of the planet, making it appear larger and closer than it truly is. Understanding these differences allows astronomers to make more informed assessments of the atmospheres of other celestial bodies. As we contemplate the vastness of space and the intricate dance of light and atmosphere, we can appreciate how astronomical refraction enriches our understanding of the universe. From the twinkling stars that inspire wonder to the planets that beckon exploration, the bending of light serves as a reminder of the complexities of the cosmos. Each observation we make is a testament to our ability to decipher the universe's mysteries, guided by the fundamental principles of refraction. In addition to its implications for navigation and observation, the study of astronomical refraction fosters a deeper connection to the natural world. The same principles that govern the bending of light in our atmosphere also apply to distant celestial realms. This interconnectedness encourages us to look up at the night sky with curiosity, pondering the incredible forces at play beyond our planet. As we gaze at the stars, we are reminded that light is not merely a source of illumination, it is a bridge connecting us to the cosmos. To further illustrate the significance of astronomical refraction, let's consider the phenomenon of the apparent position of the sun during sunrise and sunset. As the sun dips below the horizon, its light passes through an increasingly thick layer of the atmosphere. The bending of this light causes the sun to appear above the horizon, even when it has technically set. This effect is more pronounced at higher altitudes, where the atmosphere is thinner, allowing for clearer visibility of celestial objects. Observing this phenomenon can provide a sense of awe and wonder as we witness the beauty of light bending in real time. The implications of refraction extend beyond our immediate observations. They also play a crucial role in the field of astrophysics, where understanding the behavior of light is essential for interpreting data from distant galaxies and stars. Spectroscopy, a method used to analyze the light emitted or absorbed by celestial objects, relies on precise measurements of light wavelengths. Any discrepancies caused by refraction must be accounted for to ensure the accuracy of the results. This careful attention to detail allows scientists to unlock the secrets of the universe, revealing the compositions, temperatures, and velocities of distant celestial bodies. As we contemplate the myriad ways in which refraction influences our observations, we can also appreciate the role of technology in advancing our understanding. The development of space-based telescopes, such as the Hubble Space Telescope, has revolutionized our ability to study the universe. By positioning telescopes beyond Earth's atmosphere, astronomers can eliminate the effects of atmospheric refraction altogether. This has led to breathtaking images of distant galaxies, nebulae, and other celestial phenomena, providing insights that were once unimaginable. In addition to technological advancements, the collaborative efforts of scientists worldwide have contributed to our growing knowledge of astronomical refraction. International research initiatives and data-sharing platforms have allowed astronomers to pool their resources and expertise, enhancing our collective understanding of light and its behavior in various atmospheric conditions. This spirit of collaboration underscores the importance of community in the pursuit of knowledge, reminding us that our understanding of the universe is a shared journey. As we draw nearer to the conclusion of our exploration of astronomical refraction, let us take a moment to reflect on the beauty and complexity of the universe. The stars that twinkle above us are not just distant points of light. They represent the culmination of centuries of scientific inquiry and discovery. Each observation we make, each correction for refraction, brings us closer to unraveling the mysteries of the cosmos. With every gaze at the night sky, we are reminded of our place within this vast expanse and the interconnectedness of all things. In summary, astronomical refraction is a fundamental aspect of our understanding of the universe. It affects our observations of celestial objects, influences navigation, and shapes our perceptions of the cosmos. By accounting for the bending of light, astronomers can make more accurate measurements and interpretations, leading to a deeper appreciation of the beauty and intricacy of the universe. As we ponder these concepts, let us carry with us the wonder of light and its journey through the cosmos, recognizing that each moment spent gazing at the stars is an invitation to explore the unknown. As we conclude this segment of our exploration, let us embrace the knowledge we have gained about astronomical refraction and its implications. May it inspire a sense of curiosity and wonder, encouraging us to continue our journey of discovery. The universe, with all its mysteries, awaits our exploration, and the bending of light serves as a reminder of the beauty that lies within the intricate dance of science and nature. Thank you for joining us on this tranquil journey through the science of atmospheric refraction, and may your dreams be filled with the wonders of the night sky. As we gently transition into this next segment of our exploration of atmospheric refraction, we turn our attention to a captivating aspect of this phenomenon, astronomical refraction. This aspect not only highlights the interplay between light and our atmosphere, but also unveils the intricate ways in which our observations of celestial bodies are influenced by the bending of light. When we gaze up at the night sky, we often marvel at the twinkling stars and the shimmering planets, yet few of us stop to consider how much of what we see is affected by the atmosphere that envelops our planet. Astronomical refraction occurs when light from celestial objects travels through the layers of the Earth's atmosphere before reaching our eyes. As light passes through these layers, it encounters varying densities and temperatures, which cause it to bend. This bending can lead to an apparent shift in the position of stars and planets, altering our perception of where these celestial bodies actually lie in the sky. It is a fascinating reminder of how our atmosphere acts as a lens, shaping our view of the universe. One of the most significant implications of astronomical refraction is its effect on the apparent position of stars. When we observe a star near the horizon, the light from that star travels through a thicker layer of atmosphere compared to light from a star overhead. This increased distance means that the light is refracted more significantly, leading to the star appearing higher in the sky than its actual position. This phenomenon can be particularly pronounced during different atmospheric conditions, such as when the air is warmer or more humid, further influencing how we perceive the stars. In addition to stars, planets also experience the effects of atmospheric refraction. As we look at planets, especially those that are closer to the horizon, we might notice that they appear to shimmer or change in color. This is due to the fact that the light from these planets is being refracted by various atmospheric phenomena, including temperature gradients and turbulence. The result is a visual display that can be both enchanting and misleading, reminding us of the complexities inherent in our observations of the night sky.